Northeast of Australia lie the Pacific island nations of Solomon Islands, Vanuatu, and Fiji, along with the French territory of New Caledonia. Here, the Pacific and Australia plates converge to form the New Hebrides Subduction Zone along the southwestern part of the circum-Pacific Ring of Fire. This subduction zone poses earthquake, tsunami, and volcanic hazards across the region and provides a fascinating example of complex microplate tectonics. The simplest explanation of this region describes the interaction between two tectonic plates, with the Australia plate subducting beneath the Pacific plate along the New Hebrides Trench. If we nail down the Pacific plate and consider it fixed in position, the rate of motion of the Australia plate towards the Pacific plate increases south to north from 78 to 90 millimeters a year. But, as we will show, the tectonics of this region are more complex than just two major plates. As Australia plate lithosphere dives into the subduction zone, it produces earthquakes of increasing depth from west to east. Maximum depth of earthquakes is about 350 kilometers. Earthquake depths can be used to determine depth to the top of the subducting plate. Adding active volcanoes shows the line of volcanoes roughly following the 150-kilometer depth contour. This cross-section from the northern New Hebrides shows the volcanic arc about 170 kilometers distance from the trench. Melting of the asthenospheric mantle above the subducting plate supplies magma to the arc volcanoes. But a closer look at earthquakes and motions shows that this region cannot be explained by just two rigid plates. If we plot epicenters of shallow magnitude 6 and larger earthquakes from 1980 to present, we see many earthquakes, as expected, along or near the New Hebrides Trench. But we also see scores of earthquakes in the back arc area, beyond the main subduction zone. These indicate active deformation east of the volcanoes. Marine geophysical surveys of the North Fiji Basin reveal a network of back arc spreading ridges linked by transform faults. So the North Fiji Basin is not a rigid part of the Pacific plate or of the Australia plate. It is a collection of microplates between the two major plates. We already know the motion of the Australia plate compared to the Pacific plate. If we knew the spreading rates of all the back arc ridges, we could determine the motion of every microplate in the North Fiji Basin and the motion of the New Hebrides island arc with respect to both Pacific and Australia plates. Unfortunately, the spreading rates are only well known for a few back arc ridges, so this approach cannot help us to determine the motion for all of the microplates. Beginning in the mid-1990s, a network of GPS stations has been installed on islands of the region. Motions of these islands determined by GPS provide the key to deciphering the active tectonics. The yellow block arrows show the motion of the Australia plate with respect to the fixed Pacific plate. As expected, observed motions of GPS stations on islands of New Caledonia west of the New Hebrides Trench nicely agree with the Australia plate motion. Normal faulting earthquakes are found where back arc spreading ridges move the island arc away from the Pacific plate and the North Fiji Basin toward the New Hebrides Trench. In these areas, the rate of Australia plate subduction is faster than Australia-Pacific plate convergence. The D'Entrecasteaux Ridge is a high-standing and low-density feature on the Australia plate. Where it subducts, this ridge scrapes along the plate boundary megathrust and shoves the overriding central island arc to the east at an average rate of 55 millimeters a year. So here, the subduction rate of the Australia plate is only 35 millimeters a year. Eastward motion of the island arc is concentrated on a back arc thrust belt that is the site of frequent, strong, and major thrust faulting earthquakes. At the ends of the back arc thrust belt, strike-slip faults cut across the island arc. The Loyalty Ridge is another high-standing and low-density feature on the Australia plate. Where it subducts, a sliver of the arc is pushed east along a left lateral strike-slip fault. Where the southern New Hebrides Trench turns eastward, Australia plate subduction is 48 millimeters a year towards the north-northeast. Summarizing Australia plate subduction shows major variations in rate and direction along the New Hebrides Trench. Shallow, strong magnitude 6 and major magnitude 7 earthquakes frequently strike the arc and back arc areas and pose hazards from both ground shaking and tsunamis. An example is the 1999 magnitude 7.5 back arc thrust belt earthquake. During the earthquake, the GPS station on West Ambrym moved 35 millimeters east, while the shoreline on the eastern peninsula uplifted as much as 1.5 meters. The seismic data are well modeled by a thrust fault rupture zone with maximum displacement of 6.5 meters. In this cross-section, we see the fault plane projecting upward from a 14-kilometer deep hypocenter to a fault scarp observed in seafloor bathymetry. Predicted uplift of the seafloor reaches 2.5 meters and reasonably matches the observed uplift on Ambrym's eastern peninsula. This uplift produced a mound on the sea surface that spread into a tsunami, producing run-up over 7 meters high on the east shore of Ambrym Island. On southern Pentecost Island, tsunami run-up over 6 meters high destroyed most structures in a village of 300 inhabitants. Despite this earthquake occurring near midnight, only 5 lives were lost to the tsunami. Villagers, awake celebrating a wedding, well understood the risks of tsunamis following strong ground shaking and evacuated to high ground before the largest waves rushed ashore. On February 6, 2013, a magnitude 8 megathrust earthquake, the largest in this subduction zone in over 100 years, initiated at 29 kilometers depth and ruptured the plate boundary in the northern New Hebrides Trench. A fault displacement model that accounts for both seismic and tsunami observations has 2 patches of large displacement reaching over 14 meters. Seafloor uplift exceeded 3 meters near the trench, while over 1 meter subsidence occurred above the deeper part of the rupture zone. The resulting 2-meter-high tsunami crest reached the western shores of Nindo Island just 6 minutes after the start of the earthquake rupture. Along a 20-kilometer stretch of coastline, run-up reached over 11 meters high, and inundation occurred more than 500 meters inland in some locations. Over 1,000 homes were destroyed or damaged, leaving 4,500 people homeless. But only 10 fatalities were recorded. Indigenous knowledge of earthquakes and tsunamis passed from generation to generation carries the message to run to high ground when the earth shakes strongly. Understanding the microplate tectonics of this region helps to explain the locations and variety of earthquakes seen across the region.